Hello everyone, I am Tanisha. I am from BSc Chemistry Honors second year. In this video, I will read the Unit 1 of NCERT Class 11th, which is some basic concept of chemistry. So let's start. Chemistry is the science of molecules and their transformation. It is the science not so much of that one hundreds elements, but of the infinite variety of molecules that may be built from them. Science can be viewed as a continuing human effort to systemize knowledge for describing and understanding nature. You have learned in your previous classes that we come across diverse substances present in nature and changes in them in daily life. Curd formation from milk, formation of vinegar from sugarcane, juice on keeping for prolonged time, and rusting of iron are some examples of changes which we came across many times. For the sake of convenience, science is subdivided into various disciplines: chemistry, physics, biology, geology, extra, the branch of science that studies the preparation, properties, structure, and reaction of materials, substances called chemistry. Development of chemistry. Chemistry, as we understand it today, is not a very old discipline. Chemistry was not studied for its own sake. Rather, it came up as a result of two search for two interesting things. First is philosopher's stone paras, which would convert all baser metals, example iron and copper, into gold. Second is elixir of life, which would grant immortality. People in ancient India already had the knowledge of many scientific phenomena. Much before the advent of modern science, they applied the knowledge in various walks of life. Chemistry developed mainly in the form of alchemy and electrochemistry during 1300 to 1600 CE. Modern chemistry took shape in the 18th century Europe after a few centuries of alchemical tradition which were introduced in Europe by the Arabs. Other cultures, especially the Chinese and the Indian, had their own alchemical tradition. These included much knowledge of chemical process and techniques. In ancient India, chemistry was called the Rasayan Shastra, Rastantra, Rashtriya, or Rasvidya. It includes metallurgy, medicine, manufacture of cosmetic, glass, dyes, etc. Systematic excavations at Mohenjo-daro in Sindh and Harappa in Punjab prove that the story of development of chemistry in India that is very old. Archaeological findings show that baked brick were used in construction work. It shows the mass production of pottery, which can be regarded as the earliest chemical process in which materials were mixed, molded, and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery have been found in Mohenjo-daro. Gypsum cement has been used in the construction work. It contains lime, sand, and traces of CaCO3. Harpans made fans a sort of glass which was used in ornaments. They melted and formed a variety of objects from metals such as lead, silver, copper. They improved the hardness of copper for making artifacts by using tin and arsenic. A number of glasses objects were found in Musky in South India and Hastinapur and Takshila in North India. Glasses and glazes were colored by addition of coloring agents like metal oxide. Copper metallurgy in India dates back to the beginning of Chalcolithic culture in the subcontinent. There are much archaeological evidences to support the view that technologies from extraction of copper and iron were developed indigenously. According to Rig Veda, tanning of leather and dyeing of cotton were practiced during 1000 to 400 BCE. The golden gloss of the black polished ware of northern India could not be replicated and is still a chemical mystery. These wares indicate the mastery which kiln temperature could be controlled. Cotile's Arthashastra describes the production of salt from sea. A vast number of statements and material described in the ancient Vedic literature can be shown to agree with modern scientific findings. Copper utensils, iron, gold, silver, ornaments, and terracotta discs and painted grey pottery have been found in many archaeological sites in North India. Shusruta Samhita explains the importance of alkalis. The Chark Samhita mentions ancient India who knew how to prepare sulfuric acid, nitric acid, and oxides of copper, tin, and zinc, the sulfates of copper, zinc, and iron, and the carbonates of lead and iron. Rashopanishda describes the preparation of gunpowder mixture. Tamil text also describes the preparation of firework using sulfur charcoal, saltpeter, that is potassium nitrate, mercury camphor extra. Nagarjuna was a great Indian scientist. He was a reputed chemist and alchemist and a metallurgist. His work Rashtanakar deals with the formulation of mercury compounds. He has also discussed methods for the extraction of metals like gold, silver, tin, and copper. A book, Rasarman, appeared around 800 CE. It discussed the uses of various furnaces, ovens, and crucible for different purposes. It describes methods by which metal could be identified by flame color. Chakrapani discovered mercury sulfide. The credit for inventing soap also goes to him. He used mustard oil and some alkalis as ingredients for making soap. Indian began making soap in the 18th century CE. Oil of Iranda and seeds of mahua plant and calcium carbonate were used for making soap. The paintings found on the walls of Ajanta and Ellora, which look fresh even after ages, testifies to have a higher level of science achieved in ancient India. Varahimir Brihit Samhita is a sort of encyclopedia which was composed in the 6th century CE. It informs about the preparation of glutinous material to be applied on walls and roof of houses and temples. It was prepared entirely from extract of various plants, fruits, seeds, and barks, which were concentrated by boiling and then treated with various resins. It will be interesting to test such materials scientifically and assess them for use. A number of classical texts like Atharveda mention shamdai, stuff, the material used for turmeric madder, sunflower, orpiment, cochineal, and lac. Some other substances having tinting property were Kamplikia, Patanga, and Jatuka. Brahmis Brihit Samhita gives references to perfume and cosmetics. Recipes of hair dyeing were made from plants like indigo and minerals like iron powder, black iron ore, steel, and acidic extract of sour rice gruel. Gan- Ganda Yukli describes recipes for making scents, mouth perfumes, bath powder, incense, and talcum powder. Paper was known to India in the 17th century as account of Chinese traveler. Singh describes excavation at Takshila indicate that ink was used in India from the 4th century. Colors of ink were made from chalk, red lead, and minimum. It seems that the process of fermentation was well known to Indians. Veds and Kautilya's Arthashastra mention about many types of liqueurs. Charkha Samhita also mentioned ingredients such as barks of plants, steam, flowers, leaves, woods, cereals, fruits, and sugarcane for making aswas. The concept that matter is ultimately made of individual building blocks appeared in India a few centuries BC as a part of philosophical speculations. Acharya Kand, born in 600 BCE, originally known by the name Kashyap, was the first proponent of the atomic theory. He formulated the theory of very small individual particles, which he named Parmanu, comparable to atoms. He authored the text Vaishakhi Sutras. According to him, all substances are aggregated form of smaller units called atoms, Parmanu, which are eternal, indestructible, spherical, suprasensible, and in motion in the original state. He explained that the individual entity can't be sensed through any human organ. Kand added that there are varieties of atoms that are different as the different classes of substance. He said these Pramanu could form pairs or triplets among other combination, and unseen forces cause interaction between them. He conceptualized this theory around 2500 years before John Dalton's Chark Samhita is the oldest Ayurvedic epic of India. It describes the treatment of disease, the concept of reduction of particle size of matters. It clearly discussed in Chark Samhita. Extreme reduction of particle size is termed as nanotechnology. Chark Samhita describes the use of bhasm of metals in the treatment of alignments. Nowadays, it has been proved that basmas have nanoparticles of metals. After the decline of alchemy, electrochemistry reached a steady state, but it too declined due to the introduction of practice of Western medical system in the 20th century. During this period of stagnation, pharmaceutical industry based on Ayurveda continued to exist, but it too declined gradually. It took about 100 to 150 years for Indians to learn and adapt new techniques. During this time, foreign products poured in. As a result, indigenous traditional techniques gradually declined. Modern science appeared in India seen in the latter part of the 19th century. By this mid 19th century, European scientists started coming to India and modern chemistry starts growing. From the above discussion, we have learned that chemistry deals with the composition, structure, properties, and interaction of matter and is of much use to human being in daily life. These aspects can be best described and understood in terms of basic constituent of matter that are atoms and molecule. That is why chemistry is also called the science of atoms and molecule. Can we see, weigh, and perceive these entities, atoms and molecules? It is possible to count the number of atoms and molecules in a given mass of matter and have a quantitative relationship between the mass and the number of this particle. We will get the answer of some of these questions in this unit. We will further describe how physical properties of matter can be quantitatively described using numerical variables with suitable units. So let's start. First is importance of chemistry. Chemistry plays a central role in science and is often intertwined with the other branches of science. Principles of chemistry are applicable in diverse areas such as weather patterns, functioning of brain, and operation of a computer, production in chemical industries, manufacturing fertilizers, alkali acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, etc., including the new material. Chemistry contributes in a big way to the national economy. It also plays an important role in meeting human needs for food, healthcare products, and other material aimed at improving the quality of life. This is exemplified by the large-scale production of a variety of fertilizers, improved variety of pesticides and insecticides. Chemistry proves method for the isolation of life-saving drugs from natural sources and making possible synthesis of such drugs. Some of these drugs are cisplatin and taxol, which are effective in cancer therapy. The drug AGT is used for help aids patient. Chemistry contributes to a large extent within the development and growth of a nation. With a better understanding of chemical principle, is has now become possible to design and synthesize new material having specific magnetic, electric, and optic properties. This has led to the production of superconducting ceramics, conducting polymers, optical fibers, extra. Chemistry has helped in the stabilizing industries, manufacturing utility goods like acids, alkalis, dyes, polymers, metals. These industries contribute in a big way to the economy of a nation and generate employment. Being successfully synthesized, however, many big environmental problems continue to the matters of grave concern to the chemist. One such problem is the management of the greenhouse gases like methane, CO2, extra. Understanding of biochemical process, uses of enzyme for large-scale production of chemicals, and synthesis of new exotic material are some of intellectual challenges for the future generation of chemists. A developing country like India needs talented and creative chemists for accepting and such challenges. To be a good chemist and to accept such challenges, one need to understand the basic concept of chemistry, which begins start with the matter. Let us start with the nature of matter. Nature of matter. You are already familiar with the term matter from your early classes. Anything which that mass and occupies space is called matter. Everything around us, example book, pen, pencil, air, water, all living beings extra are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristic of the states of matter which you learned in the previous classes. First is states of matter. You are aware that matter can exist in three physical states: solid, liquid, and gas. The constituent particle of matter in these three states can be represented as in figure. Particles are held very close to each other in solids in an orderly fashion, and there is not much freedom of movement. In liquid, the particles are close to each other, but they can move around. However, in gases, the particles are far apart as compared to those present in solid or liquid state, and their movement is easy and fast. Because of such arrangement of particles, different state of matter exhibits the following characteristic. Solid have definite volume and definite shape. Liquid have definite volume but don't have definite shape. They take the shape to the container in which they are placed. Gases have neither definite volume nor definite shape. They are completely occupied the space in the container in which they are placed. These three states of matter are interconvertible by changing the conditions of temperature and pressure. Solid, when we heat, turns into liquid. When we heat it, it turns into gas. And gas, when cooled, turns into liquid. And when liquid is cooled, turns into solid. On heating, a solid usually changes to a liquid, and the liquid on further heating changes to gas or vapor. In the reverse process, a gas on cooling liquefies to the liquid, and the liquid on further cooling freezes to the solid. Now, classification of matter. You have learned that at the macroscopic or bulk level, matter can be classified as a mixture or pure substance. This can be further divided. When all constituent particles of a substance are same in chemical nature, it is said to have a pure substance. A mixture contains many types of particles. A mixture contains particles of two or more than pure substances which may be present in any ratio, hence their composition is variable. Pure substances forming mixture are called components. Many of the substances present around your mixture, for example sugar solution in water, air, tea, etc., are all mixture. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mix with each other. This means particles of components of the mixture are uniformly distributed throughout. The bulk of the mixture and its composition is uniform throughout. Sugar solution and air are the examples of homogeneous mixture. In contrast to this heterogeneous mixture, the composition is not uniform throughout and sometimes different components are visible. For example, mixture of salt and sugar, grains and pulses along with some dirt, often stone pieces, are heterogeneous mixture. You can think of many more examples of mixture which you have came across in daily life. It is a worthwhile to mention here that the components of a mixture can be separated by using some methods such as simple hand picking, filtration, crystallization and distillation. Pure substances have characteristics different from atoms. Constituent particles of pure substances have fixed composition. Copper, silver, gold, water, and glucose are some examples of pure substances. Glucose contains hydrogen, carbon, and oxygen in a fixed ratio, and its particles are of same composition. Hence, like all other pure substances, glucose has a fixed composition. All its constituents can be sprayed by physical methods. Pure substances can be further classified into elements and compounds. Particles of an element consist of only one type of an atom. These particles may exist as atom or molecule. You may be familiar with atoms and molecules from the previous classes. However, you will be studying about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen, etc. are examples of elements. They all atoms are of one type. However, the atoms of different elements are different in nature. Some elements such as sodium, copper contains atoms as their constituent particle, whereas in other the constituent particle are molecules which are formed by two or more atoms. For example, hydrogen, nitrogen, and oxygen. Gases consist of molecules in which two atoms combine to give their respective molecules. When two or more atoms of different elements combine together to a definite ratio, the molecules of a compound is obtained. Moreover, the constituent of a compound can't be separated into simpler substance by physical methods. They can be separated by chemical methods. Example of compounds are water, ammonia, carbon dioxide, sugar. The molecules of water and carbon dioxide are represented in figure. Note that a water molecule comprises two hydrogen atoms and one oxygen atom. Similarly, a molecule of carbon dioxide contains two oxygen atoms combined with one carbon atom. Thus, the atoms of different elements are presented in a compound in a fixed and definite ratio, and the ratio is characteristic of a particular compound. Also, the properties of a compound are different from those of these constituents elements. For example, hydrogen, oxygen, and gases, whereas the compound formed by their combination, that is water, is a liquid. It is interesting to note that hydrogen burns with a pop sound and oxygen is a supporter of combustion, but water is used as a fire extinguisher. Now, properties of matter and their measurement. Physical and chemical properties. Every substance has a unique or characteristic properties. These properties can be classified into two categories: physical properties such as color, odor, melting point, boiling point, density, etc., and chemical properties like composition, combustibility, reactivity with acid base. Physical properties can be measured or observed without changing the identity or the composition of substance. The measurement or observation of chemical properties requires a chemical change to occur. Measurement of physical properties doesn't require occurrence of a chemical change. The examples of chemical properties are characteristic reaction of different substances. These include acidity or basicity, combustibility, etc. Chemists describe, interpret, and predict the behavior of substances on the chemical basic knowledge of their physical and chemical properties, which are determined by careful measurement and experimentation. In the following section, we will learn about the measurement of physical properties. Measurement of physical properties. Quantitative measurement of physical properties is required for scientific investigation. Many properties of matter such as length, area, volume, etc. are quantitative in nature. Any quantitative observation for measurement is represented by a number followed by units in which it's measured. For example, length of a room can be represented as 6 meter. Here 6 is the number and m denotes the unit meter, the unit in which length is measured. Earlier, two different systems of measurement, that is the English system and the metric system, were being used in different parts of the world. The metric system, which originated in France in late 18th centuries, was more convenient as it was based on the decimal system. Late need of a common standard system was felt by the scientific community. Such a system was established in 1960 and discussed in detail below. The International System of Units, the SI system. In French, the system International D Units, abbreviated as SI, was established by the 11th General Conference on Weights and Measures. The CGPM is an intergovernmental treaty organization created by a diplomatic meter convention, which was signed in Paris in 1875. The SI system has 7 basic units and they are listed in table 1.1. These units certain to the 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density can be derived from these quantities. These physical quantities were length, mass, time, electric current, thermodynamic temperature, amount of substance, and the luminous intensity. The definition of the SI system are given in this table. The SI system allows the use of prefix to indicate or multiply some multiples. These prefixes are listed in the table. Let us now quickly go through some of these quantities which you will be often using in this book. Mass and weight. Mass of a substance is the amount of matter present in it, while weight of the force exerted by gravity. The mass of a substance is constant, whereas its weights may vary from place to place due to change in gravity. You should be careful using these terms. The mass of a substance can be determined accurately in the laboratory by using an analytical balance. The SI unit of mass was given in the table is kilogram. However, its fraction named as gram is used in laboratories due to the smaller amounts of chemical used in chemical reactions. Volume is the amount of space occupied by a substance. It has units of length cube. So in the SI system, volume has unit of meter cube, but again in chemistry laboratories, smaller volume are used. Hence, volume is often denoted as centimeter cube or decimeter cube. A common unit, liter, which is not an SI unit, is used for measurement of volume of liquids. 1 liter is equals to 1000 ml. In the laboratory, the volume of liquid solution can be measured by graduated cylinder, burette, pipette, and volumetric flask is used to prepare a known volume of a solution. These measuring devices are shown in the figure. Next is density. The two properties mass and volume discussed above are related as follows. Density is equals to mass by volume. Density of a substance is the amount of mass per unit volume. So its SI unit of density can be obtained as follows. SI unit of density is equals to SI unit of mass divided by SI unit of volume. So kilogram per meter cube. The unit is quite large and a scientist chemist often express density in gram centimeter cube, where mass is expressed in gram and volume is expressed in centimeter cube. Density of a substance tells us about how closely its particles are packed. The density is more, it means particles are more closely packed. Next is temperature. There are three common temperature scales: degree Fahrenheit, and the Kelvin. Kelvin is the SI unit. Thermometer is based on the scale are shown in the figure. Generally, the thermometer with Celsius are calibrated from 0 to 100, where these two temperatures are the freezing and the boiling point respectively. The Fahrenheit scale is represented between 32 degree Fahrenheit to 212 degree. The temperature on the two scales are related to each other by the relationship degree Fahrenheit is equals to 9 by 5 into degree Celsius plus 32. The Kelvin scale is related to Celsius scale. Kelvin is equals to degree Celsius plus 273.5. It is interesting to note that the temperature below 0 degrees Celsius, that is negative value, are possible in Celsius scale, but in Kelvin scale, negative temperature is not possible. Uncertainty in measurement. Many a time in the study of chemistry, one has to deal with the experiment data as well as theoretical calculation. There are meaningful ways to handle the number of conveniently and present the data realistically with the certainty to the extent possible. These ideas are discussed in detail. Scientific notation as chemistry is the study of atoms and molecules which are extremely low masses and are present in extreme large numbers. A chemist has to deal with numbers as large 600 to 200 above for the molecules 2 gram of hydrogen gas or as small as 0.000000166 gram mass of a hydrogen atom. Similarly, other constants such as Planck constant, speed of light, charge on particle, inverse number of the numbers of the above magnitude. It may look funny for a moment to write or count number of zeros involving so many zeros, but it offers a real challenge to do simple mathematical operations of addition, subtraction, multiplication, or division. With such number, you can write any two numbers for the above type and try one of the operations you like to accept as a challenge, and then you will really appreciate the difficulty in handling such numbers. The problems is involved by using a scientific notation for numbers such as exponential notation, in which any number can be expressed in the form of n into 10 is to power n, where n is a small n is an exponent with positive or negative values, and n is a number called digit term which is varies between 1.00 and 9.999. Thus, we can write 232.508 as 2.32508 in 10 is to power 2 in scientific notation. Note that while writing it, the decimal has to be removed to the left by 2 places, and same is the exponential to 2 in the scientific notation. While performing mathematical operations on numbers expressed in scientific notation, the following points are kept in the mind. First is multiplication and division. These are operations follow for the same rule which were in the exponential, that is given in the solution. Addition and subtraction, for these two operations, first the numbers are written in such a way that they have the same exponent. After that, the coefficient are added or subtracted as the case may be. Thus, for adding, exponent is made same for the both numbers, then this number can be added as follows. Similarly, the subtraction of two numbers can be done as shown below. Next is significant figure. Every experimental measurement has some amount of uncertainty associated with it because of the limitations of measuring instrument and the skill of the person making the measurement. For example, mass of an object is obtained using a platform balance and it comes out to be 9.4 gram. On measuring the mass of the object on an analytical balance, the mass obtained is 9.4213 gram. The mass obtained by an analytical balance is slightly higher than the mass obtained by using a platform balance. There, digit 4 replaced after decimal in the measurement by platform balance is uncertain. The uncertainty in the experiment or the calculated value is indicated by mentioning the number of significant figures. Significant figures are meaningful digits which are known with certainty plus one, which is indicated by writing the certain digits and the last uncertain digits. Thus, if we write a result as 11.2 ml, we say the 11 is certain and 2 is uncertain, and the uncertainty would be plus minus 1 in the last digit unless otherwise stated. On uncertainty, plus minus 1 in the last digit is always understood. There are certain rules for determining the number of significant figures. These are stated below. All non-zero digits are significant. For example, 285 centimeter, there are 3 significant figures, and in 0.25 ml, there are 2 significant figures. Zeros proceeding to first non-zero digit are not significant. Such zero indicates the position of decimal point. Thus, 0.03 has one significant figure and 0.0052 has two significant figure. Zeros between two non-zero digits are significant. Thus, 2.005 has four significant figure. Zeros at the end or right of a number are significant provided that they are on the right side of the decimal point. For example, 0.200 has three significant figure, but if otherwise the terminal zeros are not significant if there are no decimal point. For example, 100 has only one significant figure, but 100.0 has three significant figures, and 100.0 has four significant figures. Such members are better represented of in scientific notation. We can express the number 100 as 1 into 10 to the power 2 for one significant figure, and 1.0 into 10 to the power 2 for two significant figure, and 1.00 into 10 to the power 2 for three significant figure. Next, counting the number of objects. For example, 2 balls or 20 eggs have infinite significant figure, as these are abstract number and can be represented by writing infinite number of zeros after placing a decimal, that is 2 is equals to 2 point something zeros or 20 is equals to 20 point something zeros. In numbers written in scientific notation, all digits are significant. Example, 4.01 10 to the power 2 has 3 significant figure, and 8.256 into 10 to the power minus 3 has 4 significant figure. However, one would always like the result to be precise and accurate. Precision and accuracy are often referred to while we talk about the measurement. Precision refers to the closeness of various measurement of for the same quantity. However, accuracy is the agreement of a particular value to the true value of the result. For example, if the true value for a result is 2.00 gram and students A takes two measurement and reports the results as 1.95 gram and 1.93 gram, these values are precise and they are closer to each other but not accurate. Another student B repeats the experiment and obtains 1.94 gram and 2.05 gram as the results for two measurements. These observations are neither precise nor accurate, while the third student repeats these measurements and reports 2.01 gram and 1.99 gram as the result. These values are both precise and accurate. They can be more clearly understood from the given table. Addition and subtraction of significant figure. The result can't be more have more digits to the right of the decimal point than either of the original numbers. Here 18.0 has only one digit after the decimal point, and the result should be reported only up to one digit after the decimal point, which is 31.1. Multiplication and division of significant figure. In these operations, the result must be reported with no more significant figure as in the measurement with few significant figures. Such 2.5 has two significant figure. The result should not have more than two significant figure. This is 3.1, while limiting the result to the acquired numbers of substituting figures as done in the above mathematical operation. One has to keep in the mind the following points or rounding of the numbers. If the rightmost digit to be removed is more than 5, the preceding number is increased by 1. Example, 1.386. If we have to remove 6, we have to round it to 1.39. If the rightmost digit is to be removed is less than 5, the preceding number is not changed. If the rightmost digit to be removed is 5, then the preceding number is not changed. If it is an even number but it is increased by 1, and if it is an odd number, for example 6.35 is to be rounded by removing 5, we have to increase 3 to 4 giving 6.4 as the result. However, 6.25 is to be rounded off to 6.2. Dimensional analysis. Often while calculating there is a need of convert unit from one system to another. The method used to accomplish this is called factor label method or unit factor method or dimensional analysis. This is illustrated below. Example, a piece of metal is 3 inch represented in inch long. What is its length in centimeter? We know that here is the solution. Both of these are called unit factors. If some numbers is multiplied by these unit factors, it will not be affected otherwise. Say 3 in given above is multiplied by the unit factor. So 3 inch is equal to 7.62 centimeter. Now the unit factor by multiplication is done in that unit factor. 2.54 centimeter divided 1 inch in the above case, which gives the desired units. That is, the numerator should have the part which is required to be desired result. It should be noted that the above examples that unit can be handled just like other numerical unit. It can be cancelled, divided, multiplied, square, etc. Now, law of chemical combination. The combination of elements to form compounds is governed by the following 5 basic laws. Law of conservation of mass. This law was put by Antony Lavoisier in 1789. He performed careful experimental studies for combustion reactions and reached to the conclusion that is on physical and chemical changes there is no net change in mass during the process. Hence, he reached the conclusion that matter can neither be created nor destroyed. This is called law of conservation of mass. This law formed that basic for several later developments in chemistry. In fact, This was the result of exact measurement of masses of reactants and products are carefully planned experiment performed by Lavoisier. Next is the law of definite proportion. This was given by a French chemist Joseph Proud. He stated that a given compound always contains exactly that some proportion of elements by weight. Proust worked with two samples of cupric carbonate, one of which was of natural origin and other was synthetic. He found that the composition of chemical elements present in it was same for both the samples shown below. Thus, he concluded that irrespective of the source, a given compound always contains same elements combined together in the same proportion by mass. The validity of this law has been confirmed by various experiments. It is sometimes also referred to as law of definite composition. Next is law of multiple proportion. This law was proposed by Daltons in 1803. According to this law, if two elements can combine to form more than one compound, the masses of one element that combined with a fixed mass of other element are in the ratio of physical whole numbers, small whole numbers. For example, hydrogen combines with oxygen to form two compounds, namely water and hydrogen peroxide. Here, the masses of oxygen, which combine to a fixed mass of hydrogen, bear a ratio that is 16:32 or 1:2. Next is Gay-Lussac's law or gaseous volumes of Gay-Lussac's law of gaseous volumes. This law was given by Gay-Lussac in 1808. He observed that when gases combine are produced in a chemical reaction, they do some in a simple ratio provided all gases are at the same temperature and pressure. Thus 100 ml of hydrogen combined with 50 ml of oxygen to give 100 ml of water. Thus the volume that is of hydrogen and oxygen which combine bear a simple ratio of 2:1. Gay-Lussac's discovery of integer ratio in volume relationship is actually the law for chemical proportion by volume. This law of definite proportion stated earlier with what respect to mass. The Gay-Lussac's law was explained properly by the work of Avogadro in 1811. Next is Avogadro law. Avogadro proposed that equal volumes of all gases are at the same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atoms and molecules, which is quite understandable in present times. If we consider again the reaction of hydrogen and oxygen to produce water, we see that two volumes of hydrogen combined with one volume of oxygen to give two volumes of water without leaving any unreacted oxygen. Note that in figure 1.9, each box contains equal number of molecules. In fact, Avogadro could explain the above result by considering the molecules to be polyatomic if hydrogen and oxygen were considered as diatomic as recognized now. Then the above results are easily understandable. However, Daltons and others believed that at that time that atoms of the same kind can't combine and molecules of oxygen or hydrogen containing two atoms did not exist. Avogadro proposed was published in the French journal D. In spite of being correct, it did not gain much support. After about 50 years, in 1860, the first international conference on chemistry was held in Karlsruhe, Germany to resolve various ideas. At the meeting, Stanisio Cannizzaro presented by a sketch of course of chemical philosophy which emphasized on the importance of Avogadro's work. Dalton's atomic theory, although the origin of the idea that matter is composed of small individual particles called alpha tommu being indivisible dates back to the times of Democritus, a Greek philosopher. It again started Dalton's atomic theory. Although the origin of the idea that matter is composed of small individual particles called alpha atomu, meaning indivisible, dates back to the times of Democritus, a Greek philosopher, it again started emerging as a result of several experimental studies which led to the laws of mentioned above. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following. Matter consists of individual atoms. All metals of a given element have identical properties, including the identical masses. Atoms of different elements, different in mass, compounds are formed when atoms of different elements combine in a fixed ratio. Chemical reaction involve reorganization of atoms. These are neither created nor destroyed in a chemical reaction. Dalton's theory could explain the laws of chemical combination. However, it could not explain the law of gaseous volumes. It could not provide the reason for combining of atoms, which were answered later by other scientists, atomic and molecular masses. After having some idea about the terms atoms and molecule, it is appropriate here to understand what do you mean by atomic and molecular mass. Atomic mass. The atomic mass or the mass of an atom is an actually very small because atoms are extremely small. Today we have sophisticated techniques, example mass spectrometry, and for determining the atomic masses fairly accurately. But in the 19th century, scientists could determine the mass of one atom relative to another by experimental means, as he has been mentioned earlier. Hydrogen, being the lightest atom, were arbitrarily assigned a mass of 1 without any units, and other elements were assigned masses relative to it. However, the present system of atomic masses is based on carbon 12 as the standard and has been agreed up in 1961. That is, carbon 12 is one of the isotope of carbon and can be represented as 12C. In this system, 12C is assigned a mass of exactly 12 atomic masses called AMU, and masses for all atoms are given relative to this standard. One atomic mass unit is defined as a mass exactly equal to 1/12 the mass of one carbon atom. Similarly, the mass of oxygen 16O wood atom will be 15.995 AMU. At present, AMU has been replaced by U, which is called a unified mass. When we use atomic masses of elements in calculation, we actually use average atomic masses of elements, which are explained below. Average atomic mass. Many naturally occurring elements exist more than one isotope. When we take into account the existence of these isotopes and their relative abundance, percent occurrence, the average atomic mass of the element can be computed. For example, carbon has the following three isotopes with relative abundance and masses as shown against each of them. From the above data, the average atomic mass of the carbon will come out to be 12.011 U. Similarly, average atomic masses for other elements can be calculated in the periodic table of elements. The atomic masses mentioned for different elements actually represented their average atomic mass. Next is molecular mass. Molecular mass is the sum of atomic masses of the elements present in a molecule. It is obtained by multiplying the atomic mass of each element by the number of its atoms and adding them together. For example, molecular mass of the methane, which contains one carbon atom and four hydrogen atoms, this can be obtained as follows. Similarly, molecular mass of water is equals to 18.0 U. Now is formula mass. Some substances such as sodium chloride don't contain discrete molecules as their constituent units. In such compounds, positive sodium ion and negative chloride ion entities are arranged in a three-dimensional structure. It may be noted that in sodium chloride, one Na positive is surrounded by 6 Cl negative, and vice versa. The formulated formula such as NaCl is used to calculate the formula mass instead of molecular mass, as in the solid state sodium chloride doesn't exist as a single entity. Thus, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chlorine. Now is the mole concept and molar masses. Atoms and molecules are extremely small in size, and their numbers in even a small amount of any substance is really very large. To handle such large numbers, a unit of convenient magnitude is required. Just as we denote 1 dozen for 12 items, for 20 items, gross for 144 items, we use the idea of mole to count entities at the microscopic level, that is atoms, molecules, particles, electrons, ions. In SI system, mole symbol was introduced as seventh base quantity for the amount of substance. The mole symbol is the SI unit of amount of substance. 1 mole exactly 6.022 into 10 to the power 23 elementary entities. This number is in the fixed numerical value of the Avogadro constant Na when expressed in the unit per mole and is called the Avogadro's number. The amount of substance symbol N of a subsystem is a measure of the number of n specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, or any other particle or specified group electron, any other particle or specified group of particles. It may be emphasized that the mole of substance always contains the same number of entities, no matter what the substance may be. In order to determine this number precisely, the mass of a carbon C12 atom was determined by a mass spectrometer and found to be equal to 1.99 into 10 to the power minus 23 gram. Knowing that 1 mole of carbon weighs 12 gram, the number of atoms is equals to 6.02 into 10 to the power 23 atoms. Now the percentage composition. So far we were detailing with the number of entities present in a given sample, but many a time information regarding as the percentage of a particular element present in a compound is required. Suppose an unknown or new compound is given to you. The first question would ask what is its formula or what are its constituents and in what they are used, what they are present in the given compound. For known compounds also, such information provides a check whether the given sample contains the same percentage of elements as present in a pure sample. In other words, one can check the purity of a given sample by analyzing this data. Let us understand it by taking the example of H2O. Since water contains hydrogen and oxygen, then percentage of composition of both these elements can be calculated as mass of an element is equals to mass of that element in the compound into 100 divided by molar mass of the compound. Now, the empirical formula for molecular mass. An empirical formula represents the simplest whole number ratio of various atoms present in a compound, whereas the molecular formula shows the exact number of different types of atoms present in a molecule of a compound. If the mass percentage of various elements present in a compound is known, its empirical formula can be determined. Molecular formula can be further be obtained if the molar mass is known. The following example illustrate this sequence. First is step 1 to convert of mass percentage to grams. Second, convert into number of moles each element. Third is divide each of the mole values obtained by the smallest number amongst them. Step 4, write down the empirical formula by mentioning the number after writing the symbols of respective elements. Fifth is writing molecular formula. Now is the stoichiometry and stoichiometry calculation. The word stoichiometry is derived from two Greek words, stoichion meaning element and metron meaning measure. Stoichiometry thus deals with the calculation of masses, sometimes volume also, of the reactants and the products involved in a chemical reaction. Before understanding how to calculate the amount of reaction required for the products produced in a chemical reaction, let us study what information is available from the balanced chemical equation of a given reaction. Let us consider the combustion of a methane. A balanced equation is given below. Here methane and dioxygen are called reactants and carbon dioxide and water are called products. Note that all the reactants and the products are gases in the above reaction. Similarly, in case of solid and liquid, bracket S and L are written respectively. The coefficient 2 for O2 and H2O are called stoichiometric coefficient. Similarly, the coefficient for CH4 and CO2 is 1 in each case. They represent the number of molecules and moles as well taking part in the reaction or formed in the reaction. Thus, according to the above chemical formula, 1 mole of CH4 reacts with 2 moles of O2 to give 1 mole of CO2 and 2 moles of H2O. 1 molecule of CH4 react with 2 molecules of O2 to give 1 molecule of CO2 and 2 molecule of H2O. 22.7 liter of CH4 reacts with 45.4 liter of O2 to give 22.7 liter of CO2 and 45.4 liter of H2O. 16 gram of CH4 reacts with 2 into 32 gram of O2 to give 44 gram of CO2 and 2 into 18 gram of H2O. From this relationship, the given data can be interconverted as follows. Density is equals to mass by volume. Mass can be converted into moles and then can be converted into number of moles. Now the limiting reagent, many a time limit reaction are carried out with the amounts of reactants that are different than the amounts as required by a balanced chemical reaction. In such situation, one reactant is in more important than the amount required by balanced chemical reaction. The reactant which is present in the least amount get consumed after some time, and after a further reaction doesn't take place whatever by the amount of the other reactant. Hence the reactant which gets consumed first limits the amount of producing formed and is therefore called the limiting reagent. In performing stoichiometric calculation, this aspect is also be kept in the mind. Next is reaction in solutions. A major reactions in the laboratories are carried out in the solution. There it is important to understand is how the amount of substance is expressed when it is present in the solution. The concentration of a solution or the amount of a substance present in its given volume can be expressed of any of the following ways: mass percentage, mass percent or weight percent, mole fraction, molarity, molality. Let us study each one of them in the detail. First is mass percentage. It is obtained by using the following relation. Mass percent is equals to mass of solute divided by mass of solution into 100. Mole fraction. Mole fraction is the ratio of number of moles of a particular component to the total number of moles of the solution. If a substance A dissolves in substance B and their number of moles are Na and Nb, then the mole fractions of A and B are given as mole fraction of A is equals to number of moles of A divides by number of moles of solution. Mole fraction of B is equals to number of moles of B divides by number of moles of solution. Now the molarity, it is the most widely used unit and it is denoted by M, capital M. It is defined as the number of moles of solute in 1 liter of the solution. Thus, molarity is equals to number of moles of solute divided by volume of solution in liter. Now, molality, it is defined as the number of moles of solute present in 1 gram of solvent. It is denoted by small m. Molality, small m is equals to number of moles of solute divided by mass of solvent in kilogram. So here this was our unit first. Thank you very much.